Okay, we are at 19.9 magnetic fields of current loops and solenoids. Let's share the PowerPoint, and we can see that we have this loop of wire with a current in it, I, and you can see that if you just do the right-hand rule for that delta x1, the current that's in that area of delta x1, you've got current going in this direction, so you have uh, B going up, and you'll have a B1 going up through the center. And if you go to the opposite side on delta x2, using the same right-hand rule, you'll see that it's the current, you've got B1 coming up through the center. And so if you do all those delta x's all the way around, you'll get a, a magnetic field that uh, looks like it does in A, and you can compare that to a small magnet, and you can see how the shape um, that you get in a coil is similar to a small magnet. Now let's the the B produced by a coil of wire is mu zero I over 2R. Now you need calculus to get that, but we can approximate it by taking these four wires and that they essentially make a loop. You can see the green goes right to left, the orange goes down, the brown goes left to right, and then the blue goes up. So you've got four wires, and each one has a contribution of mu zero I over 2 pi r. So that you've got four of those. So if we bring the pi out, 4 divided by pi, 4 divided by 3.14159, it's about 1.27. So you can see that we've approximated it's close to the mu zero I over 2R. So that's just showing that, so B is equal to mu zero I times 2R times the number of turns. And so if you keep adding turns, you increase the magnetic field. So this is what you get when you have a solenoid. You've got these loops of wires, and each contribution, you can see if you see the little red X's, that's the current. So you do the current into the screen and using the right hand rule, you'll see that you'll get a magnetic field going up through the solenoid. If you do it on the opposite side with the dot where the current's coming out of the screen, you're going to get the same thing. You're going to get this overall contribution um, through the center of the center of the solenoid, and it ends up looking like a strong magnet. The magnetic field lines resemble those of a bar magnet, meaning that the solenoid effectively has a north and a south pole, because you can see how it resembles uh, the iron filings on this north-south magnet. So B is equal to mu zero Ni, and I think that the N in this case is the is number per unit length, N over L. Okay, so there's some applications. This is an old-fashioned CRT, cathode ray tube, and it's got. If you look at the solenoids on the top and the side, those are uh, directing uh, solenoids. The magnetic field, the changing magnetic field. Basically, what you did, you shot the beam of electrons across the screen. So that's what the electromagnet on the side does, and the one on the top makes it go from the one on the side makes it go left to right. The one on the top makes it go down. So you get this raster very fast. The persistence of vision from our eye couldn't really tell that, and it just produces an image on the screen. So that was one way of using them. There's focusing solenoids on a scanning electron microscope. That's a scanning electron microscope, and it uses focusing beams on the on the specimen that you're looking at. And then there's the Tokamak. The Tokamak uses solenoids, or it is like a big solenoid itself. Um, it has these magnetic. It produces a magnetic field inside it, so it's like a toroidal solenoid. But there's more uses to it. They use them a lot in safety devices because basically it's an electromagnet. It's an electromagnet. That means it's a magnet that's only it's only a magnet when electricity goes through it. So you use it for safety operations where let's say you have a cabinet with high voltage. You can have a solenoid that locks in place the cabinet so that nobody can open the cabinet and reach in and possibly be electrocuted. It's a safety switch that locks the cabinet. When the power goes down, the solenoid releases. You can open the cabinet and you can touch it, and everything's not powered anymore. So it's used as a safety switch. It can be used as automatic locks, where you want to quickly lock the door, you flip a switch and the solenoids will engage and lock the door. I mean, so solenoids are used in many different ways. You use the solenoids in a bell. The solenoid will activate and deactivate, and so it moves this little clapper against the bell, and you get this ringing bell. So there's lots of uses to a solenoid. Now here's Amperes law applied to a solenoid. We look at this little rectangle, 1, 2, 3, 4. We take it far enough away from the side, we won't get any. You don't get any contributions from 2 and 4 because those are perpendicular to the field lines, and the 3 is far enough outside that you don't see the contribution. So it's just really the contribution from 1. So it's the sum of B that is parallel to the solenoid times delta L equals mu 0 times I. And so that's equal to the B times the length, BL. And so B is equal to mu 0 times N over L, and N over L is the turns per unit length, mu 0 N over L times I, and that's equal to mu 0 Ni, little n, which is the number of turns per unit length. So let's, that's the end of that one. We're going to go to the last section, magnetic domains, 1910, next time. Let's see. I lost my cursor. There it is.